we discussed that finding the k nearest neighbors for a test observation can be a computationally expensive process. We have to search through all our training points to see what are the k nearest neighbors. Now, is there a better approach? Is there a better approach than this brute force method that I'm doing, that we proposed so far? We're just inspecting all our training points, figure out which ones are the closest to some test observation. In fact, we can go ahead and try to do something to help the algorithm's time complexity. And let's consider a simple two-dimensional space. One of the things we can go ahead and do is we can construct a KD tree. A KD tree is a tree-like structure that's going to create partitions in our feature space. So if I have, so I can have, let's say, points there. Let me just draw my points bigger. Some points there, maybe points there, and some points there, some points there. What I can do is I can generate partitions in this space that can box in these observations. And what I'm trying to do here is if I create enough boxes, so I start boxing my observations, what I have is a tree-like structure that I can go through and figure out where does this test observation lie in. So let's say I'm trying to make a prediction with the point that exists here. What I can do is I can just follow this tree structure, these yes or no questions that I'm building. And now, by using these KD trees, I can quickly look up what are the k nearest neighbors. So in this example here, the time complexity will be on average to look for its nearest neighbors is no longer going to be order n, but it's going to be order log of n. When I say log, I mean log of base 2. So it's going to be a lot faster to look up the nearest neighbors for this situation. Of course, you aren't always guaranteed to find the nearest neighbors. And this is an example of let's trade off some model's performance, ideally a very small amount of it, for a big gain, a big speed up in computations. The other downside of using KD trees is that you have to construct this tree structure prior to using it to make predictions, to find the nearest neighbors. And that might be a problem when you have a large dimensional space and a large amount of points. So sometimes it's helpful to use a brute force approach, and sometimes it's better to use KD trees. In fact, we can look at the documentation we have for our k nearest neighbors. You can look at the documentation. You notice here we have something called a keyword argument called algorithm, and it's set by default as auto. Let's investigate what that means. Algorithm used to compute the nearest neighbor, so we have several options. We have ball trees, which are similar to KD trees. We have the KD tree, and we have the brute force, which was the method we initially discussed for this algorithm. And there's also auto, which has its own algorithm that decides which one is best to use given the amount of data points and amount of dimensions you have. So it's usually best that we set this as a default to auto, let scikit-learn choose which one's a good approach. As I said before, scikit-learn in general tends to have a good set of default values. So I will default to those unless otherwise you want to explore, try different things, or otherwise you can change some of these other hyperparameters that you have access to when you use these models. Something else I want to emphasize is you can use the distance. Let's say I have a situation. Let's say you're trying to find, let's say these are the neighbors for a test observation. And let's say doesn't matter if I'm doing classification or regression, but let's say we're doing regression. Is there a better approach than just simply taking the mean of the labels for these 4 training points? Well, if we take the mean of all these 4 points, we're essentially saying they have equal weight. But we can go ahead and do is we can perhaps preferentially have a higher weight for the training points that are closer to my test observation. So since these 2 points are closer to my test point located here, I should weight those up when I calculate what is the value I need to predict, or what is the value I'm going to predict from my model. And since these 2 points are farther away, they're going to have a lower weight. So I can use the calculated distance to derive weights, relative weights. In that situation, what will be a good weight, or how should our weights be proportional? We can say that our weights are going to be proportional to 1 over the distance. So if it's a lot closer, it's going to have a higher weight. If it's a lot farther away, it's not going to have that much of a weight when we calculate the predicted value. And we see those options when we consider. Here there's weights, it's set to uniform. We can look and see, you can set weights as distance and see how much of a performance change you get. In fact, we can actually go and explore it, right? It's a hyperparameter. So why not investigate it? So I'm going to do there, I'm going to say CLF, weights, and I believe I have either uniform, I believe they're called uniform, and what are the options? Uniform or distance. So uniform or distance. These hyperparameters don't have to be numbers, floats. They can be things like uniform or distance in this case. They can be categories. So I'm going to create a list saying, okay, also explore whether you should use uniform or distance. Let's go ahead and run that. Okay, so I had more candidates to run, but nonetheless, it went rather quickly. Let's go ahead and plot the results. It's a little different. And let's go ahead and see what was the best one to use. So grid search, there's a best params keyword. Will tell me, or return a dictionary, the best parameter. So in this case, it looks like the model was performed better, had a lower cross-validation error or higher cross-validation accuracy when we use something like the distance to calculate the weights.